Hello everyone. So we have Sanjeevikumar Padmanaban, professor with us. Sir, am I audible? Professor Padmanaban. Am I audible?
Yes, sir.
Okay. Sir, Professor Padmanaban. Yes, sir. Sir, your voice is coming. We can. Are you facing any difficulty, sir?
Realtid. Joe for investeringstip fra Harvey. Laserdisk. Simon kan øjeblikkeligt købe. Joe kan også handle på sin mobiltelefon.
Hello.
Yes, sir.
Hello. Could you hear me? Hello. Could you hear
Yes,
me?
yes, sir. Yes, sir.
So, can I start my presentation? It's fine for you.
Okay. So, sir, let me introduce first.
It's fine.
Okay. Thank you, sir. So, Dr. Sanjeevikumar Padmanaban is a senior member of IEEE. He received Ph.D. degree in electrical engineering from the University of Bologna, Italy, and he was an associate professor at VIT University from 2012 to 2013. In 2014, he was invited as a visiting researcher at the Department of Electrical Engineering, Qatar, University, Doha, which is funded by the Qatar National Research Foundation, and he continued his research activity with the Dublin Institute of Technology, Dublin. Further, he served as an associate professor with the Department of Electrical and Electronic Engineering, University of Johannesburg. From the March 2018 to February 2021, he has been a faculty member with the Department of Energy Technology, Aalborg University, Denmark. Since 2021, he has worked as a professor with CTIF Global Capsule Laboratory, Department of Business Development and Technology, Aarhus University, Denmark. Now, we are welcome our invited speaker to kindly deliver the invited talk.
Thank you very much for the invitation and a brief introduction about me to all the colleagues of the University who organized this event. Today, I like to present something which we work from our research group in the areas of our areas on electronics and renewable energy systems, where we develop many electronics converter for the past 10 years more than. So we have done many literature reviews, and with the research group members, we have developed many configurations of its indigenous qualities and unique features. Out of which I like to present something on because today world we are focusing more on renewable energy systems and electric vehicles, because to overcome the issues of CO2 emissions. These are the major key role of many countries. So we adapted many electronics converters, how it can be adapted for fuel cell as well as towards electric vehicles and renewable energy systems, different configurations, and I can give you a comparative performance, what we develop among the standard solutions which is existing in the market, and of course some experimental validation, how we are carrying out in the lab, and what could be the future challenge will be my conclusion of the presentation. About the future of the electric vehicles, the most important is going to be the front runner will be the fuel cells, because we need a high powertrain for the electric vehicles for large scale transportations, and in this case we need to go for absolutely 100% CO2 emission free system by 2050. So we have to concentrate on all domains of transportation, either by the road or marine or space or airways. We need to look for alternative solutions based on fuel cells, because you can have a complete look how the fuel cell has been classified. There's a broad family, many classification. Most important parameter is how the temperature can be adapted between -20 degrees centigrade to greater than 800 degrees centigrade. And the power is most important. We can go for less than 50 watts to maximum less than 100 megawatts. And most important, all the goal of the nation is to adapt for electric vehicles. So we can go for small vehicles or large scale vehicles. For example, large scale vehicle, I can give an example, phosphoric acid fuel cells. So in this case, it can be adapted for 80 to 300 degrees centigrade, and with the temperature range, a power range from 1 kilowatt to 10 megawatt. So it's a simple example. Another example, I can give you zinc air battery, where it can be adapted between the temperature 0 to 80 degrees centigrade, and about the power ranges, it can be even applied less than 50 watts. That's the future, and it is adapted for small vehicles, where car or bikes, etc. With this small introduction, because as a power electronics engineers, we look for the classifications, what are the properties, how it can be adapted in real time. So that's most important, how to utilize the available renewable energy, which can provide a sufficient high power application for various ranges. So where these can be adapted in electric vehicles, that's most important. If you look at the simple model of an fuel cell based electric vehicle, we call it as a FCVS. So we have a hydrogen storage tank, fuel reformer, then fuel cell to convert these liquid into electricity in the form of direct current, so DC. And the DC available here is not sufficient enough to drive the electric vehicles. So we need an additional electronics converter which can increase the voltage from the fuel cells to a higher value. Then it is connected to an inverter which converts the DC to AC. Then we are driving the motor. Apart from controlling the propulsion system of the electric vehicle, we also have other supportive loads, luxurious needs, lightnings, etc., etc. So that's requires additional electronics converter to control a high and medium voltages. The most important factor is the efficiency, which is coming around from the fuel cell, is around 60%. So the losses is around 40%, the power generation for the DC. But if you look at the efficiency of the electronics circuits, it's around 80%. So by adapting a proper electronics converters, we can enhance the efficiency of the fuel cells output power for a complete drive system. Other possibilities is a hybrid model, which is going to be the future, because we have a main propulsion system as a fuel cell along with the battery. So we don't want to use the full fuel cell as a prime mover, because hydrogen is very expensive when compared to the conventional IC engine petrol or diesel. So hydrogen generation, we need to look for other features, so how to reduce the cost, new way of technologies to bring hydrogen costs less. Of course, the charging stations of the fuel, the hydrogen is another challenging factor in the future for the developing countries. So in this case, we need to have a parallel operation of batteries. Batteries, we have lithium batteries, but lithium battery is again a challenging factor with the lifetime and about the cost. So it can be operated with parallel operation with ultra capacitors, because ultra capacitors are like a conventional capacitors, and we don't worry about the charging state. It can start from zero, or of course it can be stored for a very long time. It doesn't depends on AC conversions, so it can be connected to the conventional single phase AC supply. We can store the energy and we can compensate the price of the battery in parallel operation. Also in these cases, we need a for electronics converter. One is a DC for high voltage generation, an inverter to control the motor. Apart from that, as I said in the previous model, we need a luxurious load which can be a medium or high voltage. Both the cases, the efficiency generated by the electronics converters are around 80%, which is a unique feature why we are moving towards more electronic based electric vehicles with fuel cell. The next important part is the transportation, because about small scale electric vehicles is fine for the domestic application in the home or etc. But for the transportation, we can't go with the same power. We need a large scale power. So in this case, we need a DC microgrids within an electric vehicle. It can be for a low duty or a heavy duty vehicle. I can give an example. In case of heavy duty vehicle, we need the fuel cell, which is going to be the main prime mover for the power generation of the DC. Then it is coupled to a DC converter to a common point of coupling, which is around the 400 to 800 volts as per the standard. And we are going to have a battery unit which is going to around the 600 to 700 volts, and we have additional DC-DC converter which can power around the 25 kilowatts, which is like a luxurious requirement in a large scale electric vehicles for the transportation purpose. On the left hand side, you can have the application. So one application, we have still 20 kilowatts AC loads, which will be pumped the power from an inverter which converts the DC to AC. Then again, we use another inverter to control the motor of the electric vehicles, both the front end and the rear end. So the propulsion system can be made. So it's a complete DC microgrid is required within the electric vehicle. What are the possibilities, solutions with the electronics converter? We have two possibilities. One is in standards, non-isolated versions where input and output are not isolated, whereas we can have another version which is an isolated version where input and output terminals are isolated by a transformer, high frequency transformer, or technically called as a coupling circuit, or isolation transformers, or many terminologies are available. Of course, these converters are called as resonant converters. So in this case, what are the possibilities in case of non-isolated version? We can have same ground, both input and output. Other possibilities, we can have floating on the load side ground point. Third possibility is to use multi-stage. For example, we can have a multi-stages, intermediate stages of DC converter cascading in the form of I say series or parallel operation, both the cases. Also in this case, we can have a common grounding, or we can have a floating ground. Same applicable for the standard solution, which is in practice with a resonant converter or isolation converter, where we can have the ground point either on the input and output, or floating on the output. Of course, we can have cascading of multiple isolated converters, or cascading of multiple resonant circuits or high frequency transformers within the input and output, and we can able to deliver the power maximum from the input to the load side. Also in this case, we can have a common ground between input and output, or floating. What are the textbook basics? So here, this is a standard converter. So this is a standard boost converter where output is larger than the input. And this configuration helps to increase the available energy from the input to the output. And this configuration is a step down converter where output is always less than the input. And this is also a step down converter, but I can say it's an inverting mode, because the diode and inductors are replaced. The location, that's the difference, just for the application purposes. But the same top three converters can be adjusted in another way by bringing the diode to the negative terminal. So the diode is shifted to the negative terminal. It is also a boost converter, but it works in a different way as a and non-inverting mode. Other possibilities, we can bring the inductor to the negative terminal. Now it's also a buck converter, I say step-down converter, but still it has its feature as a non-inverting mode. And other possibilities, we can have replacement of these diodes from the positive cycle, the positive terminal to the negative terminal. So these are the 6 possibilities. We can have different configurations of polytronic basic converters available in the literatures or textbooks to be framed for real-time application. These are in practice. But how to improve the characteristics is most important. There are possibility to increase the existing converters performance by cascading multiple passive components, because passive components are cheaper than the active components. In this case, we can look at first case is a switched capacitor, where we have 2 capacitors and 2 diodes or frame the circuit. So when the device is turned on, the energy available in C1, stored energy C1 and C2, they will be in the form of a parallel operation. So they will be added up and delivered to the load. Similarly, there are different modules where we can use the switched capacitor models. The number of circuits are shown here. The last one is an example where we have 4 MOSFETs and we have a capacitor. So it depends on the switching states of S1, S2, S3, and S4. We store different levels of DC voltages in the capacitor, and it will be delivered to the load as a very high voltage. So these are the example how switched capacitors can work in different modes. What are the possibilities? So we can able to cascade the converter in multi-stages in parallel operation and increase the load voltage. Or other possibilities, we can able to connect in series. The series combination is done and controlled by a MOSFET. We can able to deliver a maximum voltage to the load side with the enhanced power. This is one possibility. Other possibilities, we can use a switched inductor, because we have 2 passive components. One is the inductor and another is the capacitor. So in this case, we have 2 inductors, L1 and L2, and they are connected in the form of diodes. So when the device is turned on, the instantaneous energy available in L1 and L2 will be added up and delivered to the load side. So inductor is not storing devices; it has the energy in the virtual windings within the turns during the turn-on condition of the devices. But we need additional capacitors to store the energy and to deliver. So this is not shown here. So that's why these inductors are called as switched inductors. Many configurations can be framed with switched inductors by being shown here. One of the examples is this: when the device is closed, the stored energy, for example, L1, L2, L3 will be energized. When the device is turned off, the energized energy will be delivered to the capacitor C2 from L1, L2 to C3, L3 to C4, and all these stored energy in the capacitors will be delivered to the load side as a high voltage. That's why we call it as a switched inductor, because during the switching, the energy generated in the inductor is transferred to the capacitor when the switch is open. Other possibilities, we have multi-stage configurations. In multi-stage configurations is like, if you look at a very close view, this is a standard boost converter available in the literature, but we are cascading number of stages of switched capacitors in parallel. Then we enhance the power to the load side. Other possibilities, we can use a series combination. So if you use one boost converter and another boost converter are cascaded in parallel along with 2 devices for controlling for high voltage, then we are connecting series combination of switch capacitors to enhance high voltage at output. So these are the examples, and these modules are called as a diode capacitor multiplier networks or a Kraft-Walton method, because I can explain you a simple example here. You can have a look. It's a boost converter, standard boost converter. The output is clamped at the multi-level by using capacitors. So the capacitors are clamped between C1 to the maximum C2 n-1. So we can have a number of capacitors can be clamped at the output terminal, and the diode are controlling the flow of current from the source to the load, not on the reverse direction. So the input is always protected even if there is a short circuit failure happen on the load side. So based on the number of levels at the output voltage can be enhanced to higher. So this is the simplest way of increasing the output voltage in the form of a multi-stage and the output terminal by clamping the capacitors. So we have developed many polytronic configurations from our research group. So I can remember 1, 2, 4, and 5. And the middle is the standard solution which is available in the market. So we have a transformers and coupled inductor based converter family or resonant converter family. If you look at the reliability is average, the cost is very high because we need to design a high frequency transformer, and efficiency obviously very high because the maximum power is transferred from the input to the load side by high frequency transformers. Organizer, excuse me.
Yes, sir. Sorry, sir, for the disturbance.
Could you please take a control?
You can continue. Yes, you can continue, sir.
Okay, thank you. So the advantage is that high power and soft switching is the possibilities because we can deliver the high power to the load side, and soft switching is binary because when resonant converters are used, we have to look for the voltage and current switching. So technically, we call it as 0-volt switching or zero current switching if you are from the field of electronics. And of course, we can use a tunable ratio because there is a transformer. You can adjust the number of turns, and you can deliver the high power or minimum power required from the input side to the load side. Disadvantage, it's because it's having additional tank circuits. Obviously, the circuit is increasing size, so it's bulky. Maybe more losses will be generated magnetically because we use transformers. Application, it can be adapted for high power and heavy duty vehicles. If you look at the configuration, what we developed 1, 2, 4, and 5, the best among the configuration 4, what we investigated will be XY family because if you look at the reliability is very high when compared to the standard solution, and the cost is average because we use few passive components and few devices, and efficiency obviously comparable with standard solution. And the most important advantage is we use always a minimum MOSFET or IGBTs, or I say in general switches, and the structures are extended by using diodes and capacitors and inductors. The major disadvantage because we use number of diodes more, so discontinuous current will appear. But the application is most important. You can adapt for both low and heavy duty vehicles. Whereas we already investigated on switched capacitor based converter family, which can be applicable only for low duty power. Similarly, switched inductor family can be applicable for low power and low duty vehicles. And multi-level converters, I have shown you multi-level clamped converters, which can be applicable for heavy duty vehicles. So if we are looking for a trade-off between all these parameters from our own investigations, we suggest that XY family is a suitable solution for all these applications. The most important, what are the developments we are doing in the laboratory? In this case, we are looking for a converter which matches different applications. So the main renewable energy could be from a fuel cell tank, and photovoltaic panels, batteries are required because when there is a huge power generation happen on the source side, then the excessive energy can be stored in the battery. On excessive demand from the load side, we can pump from the battery to the load. So we need a suitable converter which matches between the two power flows, one from a minimum level from 24 to 48 volt DC bus, and to a DC microgrid which is around 400 volt. Of course, it goes up to 800 volt is the requirement, and the application can be for charging the electric vehicles, DC microgrids, DC home applications. Of course, we can able to power the existing AC microgrids or grids. In this case, we invented some new configuration. We call it as a 3-state inverter or tri-state inverters. Converters, because why we call it as tri-state, because we have 3 devices, 3 MOSFETs or IGBT, and these 3 devices turn on at different states. That's why we call it as a 3-state. The most important how we derive this configuration. If you look at the load side is a standard boost converter. You can have a look at standard boost converter. On the input side, we have a standard inverter. One of the legs, first leg, we replace one of the device by an inductor LX. The second leg, we replace second device by another inductor LY. Then this has become like a semi-controlled converter, but it's an inverter. We made it and merged together with additional diodes, DX and DZ and DY, so that the flow of current will be from the source to the load. And of course, this DY is controlling the flow of charge with DY. So this is the way we develop the power electronics converter by analyzing the existing solution and framing to a new dimension for high power conversion. What is the advantage of replacing these two switches by inductors? Because when the device MOSFET is closed, effects, the instantaneous energy available in LX will be delivered to the load push converter, and we can pump very large energy through the capacitor Dx. Similarly, when the device Sy is turned on, the instantaneous energy available in Ly will be delivered to Cy, and we have these two energies as a high voltage for the load side boost converter, so that we get very large voltage. So this is a simple arithmetical circuit laws, basic circuit laws of addition of voltages, and we bring a very large voltage requirement at the output. Once we design the converter, then we look at the very close performances. So we try to use all these power only between 10 to 60%. The maximum power we use only the 60%, but we bring a higher value. So in this case, when the devices are conducting between 10% to 60% of utilizing the DC bus, you are getting a gain around 42 when compared to all the existing solutions available in the literature or in practice. So once we design the converter, we have theoretical background, which is I'm not discussing here, but I'm projecting you the possibility way of how we are working on it. And then we are looking for the gain margin, then understand the unique feature, then the experimental investigation. So this is the current through the index are very important. They are periodic in nature. For example, they have a 3 levels. That's why we call it as a 3-stage. For example, if these current or non-periodic and huge spikes arises or distortions arises, all these renewable connected by this damage. So for the reliability, durability of all these devices, the current through the inductor on the input side is very essential. And this is the voltage across the MOSFET, which pumps back to 185 high voltage. You can have a look, because the input is only, we try always between a battery level like 30 volts or 24 volts to 48 volts, where the voltage across the device goes to 185, confirms high voltage has been generated. And this is the voltage across the diode, which is around the 185 volts. It confirms the unidirectional power flow from the source to the load. And the load voltage as a capacitor, we are getting 400 volt, but there is small losses which can be visualized in the next slide. Further, we develop mini power electronic circuit on these applications. As an example, fast user converter. If you look at a very close view on this one, the standard boost converter used in the practice. In the middle, between the source and the load side, we introduce switched inductors along with 2 additional capacitors, and this becomes a novel configuration which is able to provide the benefits over the existing solution and reduce loss, high efficiency. When the device is closed, the instantaneous energy available Ly, L2 will be arithmetically added up according to the circuit law and delivered to the capacitor C1, and this energy will be delivered to the load side boost converter. Apart from that, also we have an inductor on the input side. So when the device is closed, the instantaneous energy produced on the inductor will be delivered to the capacitor C1 when the device is open, and these two added up 3 voltages will be a big voltage on the input terminal of your MOSFET, so that you can able to generate a very high voltage. A simple basics of addition of 3 capacitor voltage by creating them in a parallel sequence. Once the converter is designed, we know the basics of it, and then the most important is the loss analysis, because we are taking all the components from the industrial product which is available in the market. And if you look at very closely, the losses created by the devices based on the inductors, which will be around 17 to 16%. Diode, which is around 5 to 4.8%, so the maximum goes to 5.2%, and capacitor is around 6%, and the inductor is around 9%. Most probably we are choosing the same components from the industrial make, which is readily available in the market for the purchase and replacement under quality conditions. So most probably we maintain all the losses in the converter as possible as the maximum, except the switching losses, which is varies depends upon the configuration requirements and conduction period. In this case, if you look at the capacitors C1, C2, and C3, the most important, because 2 capacitors cannot behave simultaneously the same behavior. That's why we are very cautious in looking at the capacitor behavior. All the 3 capacitors start charging from 0 to the maximum value, the same interval, with the same transient period and settling time. The most important is the internal behavior of the ripple quantum or fluctuation at the steady state, which is around 1 volt for the capacitor C1. For the capacitor 2, it's around 0.5 volts, and capacitor CY is around 2 volts, which is within the limit less than 5% of IEEE standard. What is the unique feature of this converter? The most important is we are trying to use the available renewable energy on the DC link through the conduction period of the device between 10% to 30%. So around 30% we are getting a gain around 22 times, which is pretty good than existing solution. So we verify the losses, we verify the unique characteristics of the capacitors, and we are also looking at the gains, what we can able to obtain the maximum power from the converter, both analytically, of course, with the theoretical background first. And this is an example. In the beginning, I told you we will show you some in-depth characteristics of the converter, because in electric vehicle applications, or of course if it is connected to any load requirement, the load are not fixed. For an electric vehicle, we may run at a maximum speed, then we apply the brake, then we may be traveling at low speed, medium speed, etc. So the load is regulated. So we try to regulate the converter from a maximum voltage to a minimum level as a design value we kept, where it regulates very linearly with smooth operation from the maximum to the minimum value. So in our case, we kept it around 392.2 volts. As I said in the presentation, it is not 400 because there are switching losses, conduction losses, of course, EMI and passive component losses are available within the circuit. So we are getting the losses, then we get around 395.2 volts. Then it is regulated to a minimum value 206. All the cases we keep the DC bus voltage 30 volt then the margin as a standard, and of course this is the inductor current, very smoothly regulated without any peak spikes or abrupt behavior. You can have a look here, it's very smoothly propagated, but we are showing 2 to 3 cycles. In these cases is regulated according to the load requirement, and this is the load current which is regulated according to the load what we desire. And how we obtain all these results, it's most important. The first case we need 395.2 volts. In this case we kept the switching devices, both the devices conducting at 50% and 35%. And for the second case is like 45% and 35% is the conduction period. Last case is like 35% for the both devices. So by controlling the MOSFET, we are regulating the power according to the load requirement, and very smooth behavior, that's most important, without any spikes which is created from the switching devices, because we are regulating the devices at 50 kilohertz high frequency operations. And this is an experimental setup how we have been developing our electronic circuits in the laboratory. And you can look at the size of the converter available in the board, and this is controlled by FPGA based fast digital processor, and analyzing all the results to advanced mixed oscilloscope systems. And this is the compactable size of the converter. You can have a look, and controlled by advanced drivers. In this case, if the fault appears on the component level, and it is readily replaceable because the components are designed based on the availability on the market, which is readily available for purchase. Of course, if there is a complete failure, we can easily replace because of the size is very less, like 10 centimeters, 15 centimeter diamonds, and we are making all these converters. And in more systematic way, we have shown you the results. Most important is the ripple current. What I am discussing, the fluctuation of the current through the inductors is very smooth. So we try to show you the two level of power regulation, one between 250 watts and 350 watts. The first diagram, you can have a look. All the results are taken at the standard parameters, and here the current doesn't have any huge variation. So the ripple are within the control. So we say technically ripple quantum. All the cases we kept 30 volts. The generated voltage is around 395.2 volts because near to 6 volts is the losses. Of course, this is for the response for 350 watts. As the load increases, of course, the current goes to 6.6 ampere. Also, in this case, most important is the regulation of the ripple quantum, very smooth within the standards of IEEE standards of less than 5%. Further, we also developed the other power electronic converters from the basic levels. So this is a modified circuit converter. So the basic circuit is available in the literature. it can work as a step up or step down converter at the output voltage by controlling the mass at S1. So the same configuration, by using some additional passive components, you can have a look: two diodes, one inductor and one capacitor being included on the input side from this part. Then we examining a new power electronics converter which can be able to provide you a very high power when compared to the existing solution by reduced losses and more wide range of output voltage control, where here we have a restriction to have a high power by regulating. And as a very unique feature, for example, if the device is closed, the instantaneous energy available in Lx will be delivered to C1, Ly will be delivered to C2. Summation of these two voltages will be given up to the load side boost converter, so you'll have a very large voltage. The most important, once the converter is designed, we have to look for the losses, the switch. That's in the beginning of my presentation, I said it varies from one circuit to other circuit based on the conduction and switching pattern. So here we have 47% losses from the switch. Diode is between 12 to 13%. Inductor is between 10%, and Lx is less than 1%. And C1 is like capacitor C1 is around 5%, and the combination of LZ, C2 and C3 is around 0.4%. So the most important is the power. Once we design the converter, then we are looking for the loss analysis. Then what is the benefit? That's most important. So we are looking at the power regulation from 60 to 100% of the efficiency scale. So obviously 91.4, when you are going very near to the maximum margin, we are getting 91.4% efficiency. So we are regulating the power from 60 to 100 watt scale in a laboratory scale to avoid damages, because DC power requires more fractions and complex networks. For the safety reasons, we are regulating all these converters at low voltage. One of the reasons is the cost, another one is the protection against damages. So you can ask me why the efficiency is less at the maximum value, because the converter is designed for high power, but we are regulating at a low power. Obviously, the efficiency comes down. When we are regulating all these converters to high power, obviously the efficiency goes to 96 to 97%, 96 to 97% efficiency for sure. And these are the typical results we have shown for linear operation and non-linear operation, or in terminology for electronics we say continuous conduction mode or discontinuous conduction mode. As I said in the previous slide, since we are using more diodes, the converter is not linear, and that occurs a lot of discontinuous mode of operation. That's why the second result has been presented here. The first result, we kept like a battery model, 24 volts, whereas the load regulated current is around 0.15 amperes, very smooth. There is no huge deviations or any sort of a short spike arrives. And the most important is the current through the inductor is very periodic and smooth. The ripple content is within the limit less than 5%, and the load voltage is generated around 172 volts. This is pretty good when compared to input of a battery 24. This is widely applicable for electric vehicle for microgrid application. And the most important is discontinuous mode of operation. So we can confirm with the current through the diode, which has 3 levels. You can have a look between 92 volts to 152 volts. So it has a 2 peaks. This confirms the converter is operating at a high frequency and discontinuous mode of operation. And the current through the inductor goes to the instance of 0. You can have a difference between continuous and discontinuous mode of operation. So this confirms the converter is operating at highly non-linear discontinuous mode of operation current. So most important, the output voltage still we are able to generate around 92 volts. All these results are verified with a proper theoretical original development and to show the unique features of the developed converter from the laboratory. Other possibilities, we are also looking at the converters in the standard solution. If you look at this one, the standard half-bridge inverter. An half-bridge inverter will have only 2 devices which will be conducted simultaneously opposite each other. So this converter on the load side, we couple a number of stages with 6 capacitor blocks based on as I explained in the previous slide, what is 6 capacitors. So based on the conduction period, the energy will be delivered to the capacitor and it will be added up arithmetically, and we bring a large voltage to the load side converter, which can be connected to the grid or to a motor. Intermediate stage, we can connect to the battery and we can charge the battery. Energy stored in the battery can be delivered to the load side on peak demand when it is required. So it gives you a different architecture of power application. The most important is the component selection. So in this case, if you want to have a zero stage, it means that you are going to have only the inverter, a half bridge inverter. If you want to increase the number of stages from 1 to 6, for example, 6, you are going to have 12 diodes and 12 capacitors is the requirement for this circuit. The next stage is the utilization factor or gain factor, because how to use these renewables very effectively from 10% to 90% of the conduction of the devices. So around 90% obviously you cover the maximum efficiency or maximum gain. What is the unique feature of these panels? We never use any magnetic circuit intermediate between the converter and the load side. So we don't have any isolation. Of course, under failure conditions, because of these diodes, we can't pump the reverse current flow and damage the power supply. So there won't be any possibility of damaging the input side sources when a short circuit happen on the load side because of the diodes, which is behaving as the indirection power flow from source to the load. And obviously, we can have a continuous input current or discontinuous input current. Still, we are able to generate a constant propulsion output voltage to the load side. And these converters are designed with simple passive components, and number of devices may be 1 or 2, or maximum we are going for 3 or 4. So easy to control by using any digital processes with high sampling rate for real-time applications. And these converters are simply made of enhancing the output voltage with passive components addition, and it can be easily replaceable under failure conditions with complete new configuration or components, because they are cheaper and readily available in the market. With this, I like to give you what are the challenges in the future. That's most important. The challenges are many because we have the most important is what are the performances, how we can improve the performances of your electric vehicles or renewable energy systems. That's most important. So in this case, we are going to look at how we can improve the efficiency of the EV. One possibility, we have to create appropriate or select appropriate digital signal processes in combination with electronic converters, and to adapt the modern sensing methodologies using Internet of Things sensors, of course, to move towards big data application, because in the future we are going to have many electric vehicles in the monitoring system with a lot of data. Of course, we need to adapt the big data along with optimization algorithms through machine learning or any other advanced artificial intelligence algorithms to be incorporated with electronic converter and fast sampling digital processes. How to increase the safety in the electric vehicles? Obviously, as I said in the beginning, the previous statement, we need to have a modernized sensors, and modernized sensors based on without any human interface. For example, IoT sensors to be detected what are the failures going to happen in your motors, especially from the stator, rotor, and bearings, etc. And these information should be passed on to your digital signal processor, and the digital signal processor should be having a very high sampling rate. So already pre-programmed execution statements should be executed in a pretty quick time, in a nanosecond or microsecond, as per the requirement of the processor. For example, in modern EVs, we have ABS systems and airbags, and these systems are controlled by a simple power electronics converter. In terminology, we call it as a high power actuator. So in the past, it is controlled by hydraulic systems, and expansion, and of course, occupies a lot of space, and the execution of these hydraulic systems are mechanical, so time of execution is quick lost. Whereas by using a power electronics actuator, it's a fraction of seconds, you can execute the actions for the production with ABS and airbags. Even if the power actuator is failed, it can be readily replaced by a new version because it's very cheaper. Decreasing overall cost is very important because we use number of components in power electronic circuits, by using fuel cells, batteries, etc. So, but the consumer wants luxurious needs. So, how to optimize the cost by selection of proper components that plays a critical role for all the electronics engineers to make an electric vehicle at a lower cost, but to give them a high reliability, high quality performances. How to improve the efficiency? That is very important. So in case of electric vehicles or renewable energy applications, whatever the mechanical or hydraulic parts needed to be replaced by electric motors, because they can be easily controlled by the electronic circuits for high propulsion operations. So in this case, for example, one of the possibilities is we can use IC engines along with electric propulsion. That's why we have a hybrid electric vehicles. It's a combination between IC engines and fuel cells. So fuel cells are very expansive, as you said, so the part can be compensated by the battery. So the proper selection between the renewables, fuel cells, we can able to optimize the overall efficiency of the system by choosing proper electronic components, control strategy. Apart from that, we have to concentrate on electromagnetic interference created within the electronic circuits. How to increase the durability? During my presentation, I said you the most important is the current through the inductor. I said you because it can increase the reliability of the renewables photovoltaic fuel cells or battery. In particular, battery, it is controlled by electronics converters, DC-DC converter, which makes the charging and discharging. So you should have a minimum ripple content on the input side as well as on the output side. And to keep the state of the charge is very important. Usually standards we are keeping around 90% state of the charge of the battery. So when all these parameters are maintained, then we can have a long duration of application of the battery in electric vehicle. Again, this is made all stands upon the lifespan of the electronic component, other components what we choose for the complete architecture of the network. For a electronics converter, it's very important. It also has to withstand high vibration because electric vehicles produce a lot of vibrations. Of course, if it is used in a windmill application, due to the rotation of the blades, a lot of vibration is created. So vibration arresters are very important in case of designing a electronics converter. And of course, we are going to have a large flow of current because these converters are connected in real time and used for years. Large current flows through it and can create a lot of thermal energy which has to be dissipated through proper cooling system. So we need to have a proper cooling system in the electronics converters to avoid thermal breaking. Overall, the challenges for all the electronics engineers lies between selection of a proper electronics converters and renewable energy for getting maximum efficiency, low cost. Most important, the size should be small because it can be easily replaced during the faulty condition, and it should be repeatable. With all these presentation, I like to conclude my overall scenario. We have developed many electronics converter, in particular to the focus on fuel cell based high power train systems, because the future of electric vehicles will be depends on fuel cell for all means. In this case, electronics converter based on DC to DC play a critical role because its efficiency is around 80% more when compared to 60% of the fuel cell. And all these designs, we design a proper converter which matches the load requirement of the train at different propulsion conditions. And the most important factors we consider is on cost, efficiency, and reducing the number of component requirements. And the structure is very simple with modularity and easy to control with any digital signal processor. Most important to have high frequency switching sampling rate. And with all the possibilities of converter, the future may be of using hybrid modules of DC-DC converters or multi-port. So in case of multi-port, is most important. We can have multi-input terminals of renewable can be connected in a single converter, and we can deliver a high voltage to the load side. It can be also a suitable solution because one way we can charge the battery, one way we can pump the power to the train, I mean the motor network, so that the propulsion as well as charging can be controlled simultaneously. All these cases, we always focus on the cost optimization, and most important to the eco-friendly nature. There won't be any emissions from the system what we develop, and to achieve the goals of 2050 to have a completely 100% zero emission network in all means. And thank you, one and all. If you have any questions, I'm happy to respond. If you have any questions, I'm happy to respond. Hello.
Yes, sir. Yes, sir.
If you have any technical questions, I'm happy to respond.
Okay, so you can share your screen, sir.
Sorry.
You can share your screen, sir. Yes. Do you face any difficulty, sir? Are you
Yes,
facing?
I already shared my screen. Yes. I don't know what is going on your side because I am presenting from here. I'm looking all is fine. Could you able to see my screen? Hello. 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 Hello.
Yes, sir. Yes, sir.
So I finished my presentation. If you have any technical questions, I'm happy to respond.
Sir, am I audible to you, sir?
Yes.
Okay. So you are also audible and your screen is showing, displaying.
Okay. If you have any technical questions, I'm happy to respond.
Okay. Okay, sir. Okay, sir. Now you can continue, sir.
Actually, I finished my presentation. If you have a question, I'm happy to respond. Hello.
Yes, sir. Pardon, please, sir.
I finished my presentation. If you have a question, I'm happy to respond.
Sir, your voice is breaking.
Actually, I completed my presentation. If you have a question, I'm happy to respond. Because I don't know what is going on your side. So I completed my presentation.
Okay, sir. Okay. So participants, if you want to ask any question, you can unmute yourself and please ask. So this now session is open for the question answer. So if you have any question related to the power electronics and their application and related to the presentation, you can ask, free to ask, please.
Hello.
I think, sir, there is no question.
Hello.
Okay.
Are coming from the participants.
Hello.
Yes, sir. Yes.
I'm not hearing anything.
Yes, sir. Yes, sir. Please ask.
Hello.
Yes, sir. You are audible. Please ask.
Any questions or I can wind up?
Yeah, yes, sir. Actually, the participant is facing some difficulties, so he has joined now.
Hello. Hello.
Yes. Yes.
Is the technology which you have discussed is being used in the present electric cars?
Obviously, yes. With conventional modules, yes, but not with the advanced configuration what we develop, because we are looking at the current scenarios and we are developing a new module. So currently we are using mostly on the existing electric vehicles, especially what have been developed in India. or based on diode configurations, because it's much cheaper to convert directly the AC to DC. But it's not sufficient, because in the future we are going to have many electric vehicles. Then the controlling and the pollution of the grid is a big challenges, and of course the charging infrastructure. In this case, we need to develop new power electronics configurations, new microgrid models which can optimize all these parameters.
Okay, thank you.
Okay, any other question? Okay, I think there is no more question.
Yeah.
So, yeah, yes, sir. Yes, sir. So, once again, I would like to thank our invited speaker, Professor Padmanaban, sir, and please receive our token of love. We are expressing our gratitude for gracing this occasion and for delivering such an informative talk on power electronics. So thank you, sir. Thank you for joining with us.
Thank you. Thanks a lot for your invitation, and have a nice day ahead, one and all. I wish you all great success. Bye.
So I am requesting you all to please join with us at 2 p.m. And Dr. Danilo will join for an informative talk. He is from the Italy. So now we are going to close this session, and this session will again open at 2 p.m. Okay, thank you all. Thank you for the active participation.